All right, so we're back for more. Let's get back to our review. And we're going to pick it up where we left off with our discussion about symmetry of a graph. So here we're going to see the formal definition of how to determine if a graph is symmetrical or not. Okay, so there's the three basic types that we might encounter, as we mentioned earlier. So from left to right, as you can see here with this parabola. And how do you know that it's symmetrical? Because for every x, y point on the right of the axis, that is, there is going to also exist the point negative xy. So in other words, if the point, let's say 2, 2, 3 is over here, then it guarantees that negative 2, 3 is over here somewhere. So the symmetry is from left to right. Or we could say more formally with respect to the y-axis, okay, because the y-axis is the dividing line between the left and the right-hand side. From top to bottom, or with respect to the horizontal axis, which we can also call x-axis symmetry, if there exists a point xy in the first quadrant in this case, then in the fourth quadrant, there's guaranteed to be the point x negative y. So in other words, if this is the point 3, 4, and we know that down here we'll find the point 3, negative 4. Okay, and then as far as the axis, the origin goes, rather, the way it works now is that if we find the point xy, let's say that's 3, 5, we're guaranteed to find the point negative 3, negative 5 in the opposite quadrant. Okay, so that's how you would know. Now, these are just individual points. It should be possible to algebraically show that no matter which point we're referring to, we can find the other version as well. So, for example, here's an example they're going to show us. Here's 2x to the fourth minus x squared plus 2. Actually, I'll tell you what, let's start with a slightly simpler case. I just want you to see a very simple one first, and then we'll get back to this one. This one's bound to be a little bit more involved. Let's just take a simple case like y equals x cubed. And then, of course, we already know that this is symmetrical with respect to the origin. So that means that, again, if xy is here, then we know that minus xy is here. So in other words, they're both the negative of the first point. So you're probably wondering, well, how can we prove it for every single one of these points? Well, here's what we would do. Replace x with negative x. So that would give us negative x cubed. So if y equals x cubed, that means that negative y would be negative x cubed. And that simply means that, let's see, actually, let me fix this. This should have been inside here, sorry. That's better. Okay, in other words, this is showing me that for every whatever point we had originally, the negative x will be in that other side in the third quadrant. Okay, so it doesn't matter what point I pick, whether it's 2, 8, 16, it doesn't make any difference. So for example, let's just quickly double check this. In this case, we'd have the point 2, 8 in the first quadrant. Down here, negative 2 would be corresponding to negative 8. All right, now let's look at this one. Now, by the way, this one has an exponent of 4. Okay, and that indicates that this graph, whatever it looks like, is going to look similar to a parabola. Okay, so in other words, when the highest exponent is 4, you're going to expect to see symmetry from left to right. And so let's see, first let's go into Symbolab and see what this actually looks like. Let's see, where is it? Let's try. All right, so is it 2x to the 4 minus x squared plus 2. Yeah, so even though, I mean, the behavior is a little bizarre, but you can see it does somewhat resemble a parabola, and you can see the symmetry very quickly and easily. What's going on the right-hand side and the left-hand side are mirror images of each other. Um, but, oh, okay. I guess that's all they wanted us to do. Now this one is different because the highest exponent is an odd number. Okay, when that happens, what you're going to see is that you're more likely to run into symmetry with respect to the origin, not from left to right or from top to bottom. You're most likely to encounter symmetry between the two opposite quadrants, or in other words, with respect to the origin. So 2x cubed minus x looks like this. Yeah, so you can see it's very clear that you've got symmetry across the origin. In other words, the first quadrant and the third quadrant are in fact mirror images of each other. So they're not actually asking us to prove it algebraically. They just want us to notice the the graph was showing us exactly what we need to know. Later on, oh, here they, oh wait, they are asking us to do it. Okay, well, what do you know? All right. So in other words, what they're saying is try this. On the left-hand side, we're going to replace all the x's with negative x and see how the new function compares to the original one. So if you notice, like here, for example, this x cubed becomes negative x cubed, this x becomes negative x. And so when you cube negative x, becomes negative x cubed. So this is the new function. This is the original function. Okay. So if you notice, the two of them are not equal to each other. And so what that means is that we do not have symmetry with respect to the y-axis. Another way to write this would be this. Right, so there's instead of y, we could replace that with f of x. The argument inside tells me what value of x I'm using. So because those two are not equal to each other, that means that we do not have symmetry with respect to the y-axis, which you can see for yourselves in the graph. What's on the right and the left are not the same, of course. But with respect to the origin, if you remember from the way we defined this, let's go back a bit. Here, for each xy, we have to have negative x, negative y. So what we're looking for is this. To prove that this is happening here, what we have to do is replace each x by negative x, each y by negative y, and we should end up with the same result. Okay, and that's exactly what happens here. And that indicates that we do, in fact, have a geometric or algebraic proof that this graph is symmetrical with respect to the origin. Okay, there it is. Points of intersection are easy. We know how to do this. But we're used to seeing it done with respect usually to two linear functions. It's also possible to find intersections between functions that are not necessarily linear. Here, for example, you can see that we've got a parabola and a linear function or straight line. And it must be the case, unless that line is actually tangent to the parabola, it's going to intersect the parabola at two different points. The question is, what are those points? Okay, so in other words, if we had this situation, or we could have this situation, if this is our straight line, whoops, let me try that again. All right, let me put it down here somewhere. It's possible that they don't actually intersect at all. All right, right here, this line just simply touches on the problem, but here instead, the example they gave us is x squared minus y equals 3. Now, the way they've written it, we could rewrite this as and then we know exactly what it should look like from before. We know that it's facing up because the coefficient of x squared is positive, and we know that the intersection, the vertical intersection that is the point 0, -3. Then the straight line they're giving us is x minus y equals 1. And so the intersection or the intercept here is 0, -1. Okay, now they want us to find these 2 points. And so in order to do that, we're simply going to set the 2 equations equal to each other. So actually, we should probably rearrange it. It's clearly a quadratic expression. So let's do this. Let's subtract from both sides. And now we can either factor this or use the quadratic formula. But if you remember how to factor, this one is very straightforward. If you can double check that with FOIL. And so this implies that x equals 2 and x equals -1. And of course, in order to find the y coordinates, we can plug these results into either of these 2 equations. So let's do the y equals x minus 1. Okay, so one of the 2 points of intersection is 2, 1. And over here, so the point -1, -2 is the other point where these 2 curves or functions intersect each other. Okay, so now my graph isn't drawn as well as it might be. So let's look at theirs. 2, 1, -1, -2. Perfect. Okay, so really it was just a simple matter of setting them equal to each other. And here's another one. Oh no, this is that one. Sorry, this is the one we just did. So you can see what they've done. They took the 2 and they set them equal to each other and solve for x, both values of x, and then they were able to find y by plugging them into either of the 2 original equations. All right, so here they're going to briefly discuss mathematical models, some ways in which we can use math to represent real-world variables. Like here, they're looking at carbon dioxide using a quadratic equation. And what you can do is you can use this as a prediction. Now, whenever you have a model like this based on time, you have to be careful. You're not going to use the actual years in this model. We're going to use, if the starting point of our data is 1990, that means the time equals 0 will be 1990. And that means that the year they're actually interested in, which is 2035, would be the year 45. So if we want to forecast for the year 45 or 2035, then all you would have to do is plug that in for the t here, and you get your result. Oh, wait a minute. Then they just changed it to 1960. Why did they do that? All right, well, if 1960 is year 0, okay, wait a minute. Now, this is a different example, I guess. Here, year 0 is 1960. and they're trying to predict 2020, that's clearly going to be year 60. So then you plug in 60, you have y equals 0.13, 0.0113, sorry. And then you pop that into your calculator and you should get approximately 480.2. All right, so we did a bunch of these examples in pre-calculus. That was that part. All right, so there's a couple more parts here that we want to cover. So the next one, P2. All right, linear models and rates of change. Now, I have to tell you right up front, this is going to prove to be really, really, really important in Calc 1. All right, linear models, rates of change. You're going to see a lot of this discussion in the next first couple of chapters. Not that what we were just doing wasn't important, but this is really going to be the foundation for a lot of what's coming up next. So, and of course, we understand how a slope works. We've got the 2 points. We can solve for the slope. So y over delta x. Whoops, what did I do? Now, keep in mind, it actually doesn't make any difference which point is considered to be 0.1 and which is 0.2. You'll get the same result either way, right? So the deltas are simply the changes. Delta, this is the Greek letter delta, of course. It's always used to represent change in math. And so it's the difference between the two y's divided by the two x's. And sometimes you remember from high school, sometimes they call this the rise over the run. If that helps you remember, that's fine. But it's delta y over delta x is the slope. Okay. And then they've got a couple of simple examples here. We can go. Okay, I think we can do that. Except I mentioned this earlier. The one case you have to watch out for is if the line is vertical, then the slope is undefined because with a vertical line, the x is a fixed constant. So that means the slope is delta y over 0, which of course is undefined. We all know that the one unbreakable rule in math is that you cannot divide by 0. I don't remember what year you were taught that, but this is one of the things that you must never do in math, divide by 0. All right, so then they're going to use this to help us derive the equation. Now, by the way, if you remember, most of the time for straight lines, we use the equation y equals mx plus b. It's sometimes called the slope-intercept form. This is the one that we're used to, but it's also possible to write an equation like this of a straight line. This is known as the point slope form because it contains the slope and it contains the point x1, y1. This one the name is pretty straightforward because it contains the slope and it contains the intercept. And of course, the two are perfectly equivalent to each other. It's no different than expressing a temperature in Celsius versus Fahrenheit. It means the same thing. But again, yes, most of the time we're going to run into this form. So like here's a quick example. What if, imagine they told you that a line has a slope of 3 and it has a point 1, -2, then you know that the equation is. So just keep in mind, this is of course x1, this is y1. And if you feel so inclined, you can rewrite it in the slope intercept form that we're much more familiar with by subtracting this 2 from both sides. And that's our final result. Let's see. All right, let's try this example. They're trying to show some real world examples of rates of change. So Texas's population. Now here they're using the actual years. It doesn't matter because we're calculating differences. For other situations, you always use 0 for the first year, and then you add to that as you go along. But here, in the denominator, they only need to know how many years have elapsed. In this case, from 2010 to 2020. So they're going to leave the years the way they are because the denominator will simply be 10. The population went from 25.2 to 29.4. In other words, it went up by 4.2 million. And that means that on average, the population is increasing at a rate of 0.42 million people per year in the state of Texas. Now, chances are it didn't go up by exactly that much every year, but on average, assuming that the growth rate is linear, then this is what it works out to be. And so, oh yes, so they're showing you that, oh, they're doing a forecast. Okay. If the growth continues to be 0.42 every year, then 8 years from now, that would bring us to 32.8 million people. Okay, so again, we're making an assumption here that the growth rate is linear and the slope or the rate at which the population increases is 0.42. If that's really true and it continues in the future, then it would be an easy matter to figure out the population in 8 years. All right, so I think we understand how this works. And you can see there's actually at least one other way of expressing the equation of a line. You run into this every so often, but I don't think it's terribly useful. Yeah, I mean, this is what we're used to seeing. Quick review here. Parallel lines simply mean that we have two straight lines that have the same slope. Perpendicular is an interesting one because they meet at right angles. Okay, remember this little symbol indicates this is a right angle. And hopefully I haven't forgotten that that's 90 degrees. So they meet at right angle. And the way you can prove that algebraically is if the product of the two slopes is -1. Okay, so you can write this in a couple of different ways. For example, I'll just quickly make an example right now. Are the lines y equals 2x minus 4 and y equals -1/2x plus 9 perpendicular? And the answer is yes. So, you can easily imagine here's y equals 2x minus 4. Here's, and yes, they cross at right angles. So let's see, what do they want us to do here? Find the general forms of the equations of the lines that pass through the point 2, -1 and are parallel to this first one and perpendicular to the second one. Yeah, so what they're trying to do, basically all they're saying is that if you write these in their normal forms, Wait a minute. Something's not right. Um, no, this one is wrong. Sorry. This one is negative. They're both, they're both the same line. Well, that, I'm not sure what they're getting at here, but whatever they're looking for, they'll have a slope. This line will have a slope of 2/3. Whatever line they're looking for here will have a slope of -3/2. That's the only way they can be perpendicular to each other. Okay, so what they're doing is they're taking the point slope form and they're replacing the slope with 2/3 and the point they gave us, which is 2, -1, which leads us to this equation. And for the second one, they're replacing the slope with -3/2 and they're substituting in the same point. So this is what it ultimately looks like. So these are this is the original line, by the way. So what they wanted us to do is find a line that's parallel and crosses to the point 2, -1. And then here they wanted a line that's perpendicular, but also crosses to the point 2, -1. And that's what this was all about. All right. Well, that was the second part. So let's go get the third part. So, this doesn't this won't take that much longer. We'll be ready for the new material quite soon, as a matter of fact. Um, let me just go get the third part of this. This is it. Preparation for calculus, functions and their graphs. All right. So, here's some basic review of function notation. We understand relation between two sets is simply a set of ordered pairs, as we discussed earlier. And a function is relation has that extra property that each x is uniquely associated with a unique y. Okay. And so let's say we have something like this. So you can draw this, these special graphs. Let's say we have a very simple case. The domain of x is simply 1, 2, and 3, and y has a domain of, let's say, 2, 4, and 6. So clearly this is a function. Each x is associated with one and only one y. Let me show you a couple of other cases where they are not functions. Oh, actually, that's not what I wanted to do. So this one is not a function because if you notice x equals 1 is associated with both y equals 1 and y equals 2. So this doesn't work. Here's another one that doesn't work. Okay, so this one doesn't work because x equals 3 is not associated with any value of y. So these two, this is a function. These two are not functions. Okay, and it's again because of the fact that each x has to belong to one y. Now, the order of them doesn't really matter. In other words, it might look like, because of the way I've drawn these, it has to be one goes to two, two goes to four, et cetera, et cetera. No, like for example, this is fine. There's no problem there. This is also a function because again, each x is associated with a unique y. Okay. But the problems arise when you either have, you see like here, this x1 equals 1 is associated with both y equals 1 and y equals 2. And over here, x equals 3 is not associated with any of the y's. So neither of these are functions. This one is fine, and so is this one. Now, of course, I'm sure nobody's forgotten that in these cases, y is defined as the dependent variable, x is the independent variable. So in other words, what that means is that x is sorry, y is a function of x, not the other way around. Okay, so that's how that works. So whatever x is, it determines the value of y. It's not the value of y that determines the value of x. So for example, actually, let me write it like this. In other words, your weight depends on your height. It's not the other way around. So therefore, in that case, x is therefore independent variable, and y is the dependent variable. All right. Now, a function, notice how they just made, they want to make it very clear. They're talking about real numbers here, the real valued function. They just want to leave out the possibility that that we're dealing with imaginary numbers. In other words, um, real valued function not take on any imaginary values. And if you remember from, again, your previous travels in math, an imaginary number is something like this. The square root of -1 is defined to be I, and this is what we mean by an imaginary number. Now, if we were to combine real and imaginary numbers, like something like this, then it's usually known as a complex number. Okay, because that is a real and an imaginary component. But here we're restricting our attention, at the least at the moment, to what are called real value functions, which means that the domain and the range can only be real numbers. Okay, so the domain, going back to those graphs I showed you earlier, the circle on the left, which is intended to show the values that X can assume, this is the function F, which associates each of these X's with these Y's. Okay, specifically, this is the function f of x equals 2x. But here, the domain is the numbers 1, 2, and 3. This is the range. Okay. Now, a lot, and you may remember from pre-calc, a lot of time was spent trying to identify the domain and the range of a function. Um, there's a lot of rules that we can learn to help us figure out what the domain is and the range, but just be aware that the domain is simply all the x's that do not result in either division by 0 or possibly an imaginary number, because these are meant to be real valued functions. We're excluding, at least here, at least, the possibility of imaginary numbers. So, and the same thing with y, all the output must be real numbers. We can't have any imaginary numbers in the range. So not for a real valued function, that is. Now, they're also introducing a couple of other concepts. Image basically is the set of numbers that the domain could potentially take on. So like, for example, here, the domain goes into the range. I guess that's all they're going to tell us, huh? Anyway, so they just briefly mentioned the word image. The image is supposed to indicate like even if you're not using not all the values can possibly be in the range, at least the real numbers themselves could be considered the image. So anyway, where do we leave off? Well, anyway, all right. So, oh, okay. So this is something that will come in important later on. Um, usually when we write an equation, we've got y on the left, x and the constants go on the right. It doesn't have to work out that way. Uh, so they're introducing this notation implicit. Um, what they're getting at is this. When the x's and y's are all bundled together like this, um, they're saying that y is implicitly defined because the expression is not directly showing y as a function of x. Whereas over here it is. So here we say that think I spelled it wrong. X is Y is explicitly defined as a function of X. Meaning that Y is on the left-hand side and the X and the constants are on the right-hand side. So this is the distinction they're drawing. On the left over here, the X's and Y's are all together. So while Y is being defined as a function of X, it's only implicit, it's implied. We don't know what that direct relationship is. On the right-hand side, we do. Now, the only reason this ever matters is because there are going to come equations where it's not really possible to split up the two variables from each other. And so can't think of any examples off the top of my head, but when that happens, then solving for the equation is a little bit more challenging. Let's put it that way. Here they're introducing the idea of evaluating a function. Basically, all it means is to say, listen, write out the function in this form, explicit form like this. And whatever we're looking for, solve for that by replacing all the x's with this, whatever's in the parentheses. So you're just replacing all the x's with whatever you see in the parentheses here. So here it was done without an actual numerical constant. Well, all right, I'll tell you what, let's try f of 5 or something like that. Okay, so here we don't know what this is unless we're told the value of a. But a lot of derivations in calculus are actually done this way, where we have a variable that we can replace with a constant somewhere else. And so we do need to have some skills in evaluating functions using these unspecified constants. Like here's a classic example of this. This expression is going to show up very, very soon. It's going to prove to be extremely important. And so they would like you to get a little practice here. In fact, why don't we move on to this document and see what we can make out of it. We have f of x equals x squared plus 7. And they're trying to evaluate it at x plus, even more than that. They want to know f of x plus delta x all over delta x. Now, this seems like an odd choice, but soon enough, we'll be seeing this all the time. So the f of x is easy. Let us figure out what to do about this f of x plus delta x. So if you notice, what happened was the x was replaced with x plus delta x. Now, of course, we have to square it. Now, here you've got a couple of choices. This will depend on what, probably, I guess, what math classes you've had before. I would have been, in my day, we would have been shown how to do this using this technique called FOIL. Whenever you have a setup like this, where you're multiplying two binomial expressions like this, you can use FOIL. And I've been told in my classes that there are people who've never heard of this name, FOIL, before. It's an acronym. It just means you multiply the first terms, the outer terms, the inner terms, and then the last terms, and then just add them up. So now this, as far as this expression is concerned, we're going to replace that first part with this very messy expression, x squared plus 2x delta x plus delta x squared. Then we subtract the original function, which is x squared plus 7, and then divide by delta x. So now we're going to have to be very careful here. Because we're subtracting, so that means we have negative x squared and minus 7. Now, as it turns out, usually in this type of situation, there's going to be a lot of cancellation. And so you can see we're going to lose let's see what terms we're going to drop these out. Huh. I thought there'd be more cancellation than that, but I guess not. Okay. No, I think I must have done something wrong. Hold on a second. Yes, I did. You know what I did? I forgot the 7. When I applied the FOIL, I forgot the 7. Yeah, that's right. Well, that explains that. Okay. So let me put that back where it belongs. Much better. Okay. So we got 2 cancellations. And we're left with 2x plus delta x. Okay. So that is the result of this messy expression applied to x squared plus 7. And again, right now you're saying, what in the world are we supposed to do with this? You'll see in I think chapter 3 what this is for. All right, so you can see why they're using this as their example. All right, the domain and range. So it says here that we can describe the domain either explicitly with an equation or a number or something, range of numbers, or some kind of an equation. So the implied domain, it says here, is the set of all real numbers for which the equation is defined, whereas the explicit one is given with the function. Ah, all right. I mean, it seems like all right. I'd actually not seen it described this way before, but so what they're saying here is that in this case, you were told in the problem that this is the domain, which means they're calling it an explicit domain. Whereas here we had to figure out for ourselves that x equals 2 or negative 2 result in division by 0, which means they can't be part of the domain. Now, as far as the domain goes, there's a couple of different ways we can write it. If you notice here, and Simulab uses this approach too. They're just saying here x is any x, meaning any real x, except the numbers plus or minus 2. But in some books, they use what's called interval notation. Oh my God, what happened there? And when it's so in other words, they're saying that x is all x's such that x is not equal to plus or minus 2. If you look at the real number line, this is what they mean. It's everything from negative infinity up to, but not including 2, negative 2, negative 2 up to 2, not including either one, and 2 up to infinity, not including the 2. So to write it in the interval format, you would write. Now, if you notice, those U's are the union symbol, which means you're combining sets. These are infinite sets, by the way. So the first one is everything from negative infinity up to negative 2, but not including the negative 2. And in the middle here, we have negative 2 up to 2 without either of the endpoints. And then at the end here, we have 2 up to infinity, again, without the 2. So this is somewhat more complicated way, I guess, of expressing the idea that all real numbers are in this domain except for the negative and positive 2. Okay. So we should be really used to either form of writing this, because you never know when you're going to run into these. Oh, here's an interesting one. Remember, the domain cannot allow for any x's that lead to an imaginary number. That means that the number under the square root sign can never be negative, which means that the smallest number x can be in this case is 1. Because if x is 1, then the square root is 0. If x is 2, then the square root is positive. So what we end up with is this. So there's the square root function increases at a progressively decreasing rate. It starts here at 1, 0, and that means that the domain is anything from positive 1 to infinity, including the 1. All right. So remember, so the 1 counts. Everything above that is fine. We are leaving out anything that's smaller than positive 1, rather. Okay. Now, as far as the range goes, you can see that whatever comes out of the square root sign cannot be negative. So the range is everything from 0, including the 0, up to infinity. Okay. So that's how that's done. And here's another similar one. You can see, well, it's a little bit more involved because you're subtracting this x squared, but x can equal to, well, actually, it can equal negative 2, and it can equal positive 2, and it can equal anything smaller than that. Okay. But that's as far as it can go. In other words, once the absolute value of x goes outside that range, then we have a problem. For example, 3 would give us negative 500 the square root sign, but 1 is fine, 0 is fine. So the domain is everything between these two, including the two endpoints. So we would write it like this. Everything from negative to positive 2 and everything in between. So if you want to look at a graph of this in Symbolab, just to convince yourself this is right, yeah, that's an interesting function. It's a little semicircle, I guess you could call it, that's only defined over the interval from negative to positive 2. Okay. And if x is 0, the function reaches its maximum value of 2. So the range, if they ask for it, would be everything from 0 to 2, including both endpoints. Right. Now, functions, there are special types of functions. In other words, we know what a function is now. All the x's are associated with a single y. But there's a couple of special cases. The one-to-one is particularly important because, let me show you what that's all about. Okay, so this one is a function. It's also one-to-one because each x is associated with a single y, but each y is also associated with a single x. Okay, that's not true over here. It's a function, but it's not one-to-one. Because both x equals 1 and 2 are both associated with y equals 1, and that means it's not one-to-one. So now let me give you a real world example of this that I think you'll find that helps understanding this. Say a function that associates people with birthdays is a is not one-to-one because more than one person can have the same birthday. So we're assuming that people are X and birthdays are Y. On the other hand, a function that associates people with social security numbers, that's a different matter altogether, isn't it? Because everyone has a unique social security. So in other words, if you look at these graphs, you can see if I replace these numbers, if these Y's are social security numbers, two people can't have the same one, but they can have the same birthday. Okay, so that's the distinction between the two cases. To be a function, each x is associated with a unique y, but it doesn't have to be both directions. With one-to-one, it does. So we'll see later on why this is so important. But so we got some interesting questions here about graphs, some basic classifications of different types of functions, and composite functions are coming up. And then in part 4, wow, I wonder what's in there. It's afraid to show it to us. There we go. Oh, our old friend, the trig functions. Now, I have to tell you, here you can get some help from a calculator. Also, there's a couple of tables that I have here somewhere that I think I'll post on here because they could potentially be very helpful. They're basically little charts that help us identify trig functions without having to look at a calculator or a computer or something. So anyway, so I'll tell you what, I guess it looks like it's time to stop here. So when we pick it up again, what we're going to do is focus our attention on more discussion about graphs of functions, different types of functions, composite functions, and then trig functions. Okay. And then we'll be ready to start Calc 1. Okay. So um, I don't know how much longer that'll take. Probably one more full session and possibly a little bit of the next one. But when we're done, hopefully all this stuff will be fresh in your memory. And, even as we go along, if we run into something that you haven't thought about in a while, we can certainly review it. So anyway, all right, we'll stop here. And I guess we'll pick it up next time with our continued discussion about graphs. Okay, so I'll see you then.